All right, guys, let's start. Sorry for a slightly delayed start. Just took a little bit longer than usual to get it set up. All right, so as we did yesterday, I'll continue today by presenting a few of the questions because you guys should get some practice in seeing how to think about the basics of limits, of functions, and so on. And please do pay attention. We'll have some time to talk to each other. So we'll do quick presentations for whatever we don't get through today. You'll have some chance tomorrow to talk to each other, use the mate system, figure out the remaining questions, and then we'll see what to do tomorrow. Okay. But today, let's do maybe 2, 3, 4 more questions and see how to proceed. Okay. So yesterday I talked about the first 2 questions, which are to do with sets of numbers. Now let's do a few about sequences and their convergence, limits, see how to think about these things. Okay. So first of all, like question number 3 is to do with the limits of sequences. So in this case, like the sequence is Sn is n plus 1 over 2n plus 1, and you have to show that it converges. Okay? You have to show that such a sequence converges. To show that it converges, what is the definition of the convergence of the sequence A? So question number 3a, for a sequence to converge, 3a, so if Sn is equal to n plus 1 over 2n plus 1, if this sequence converges, so first of all, when we say a sequence converges, we are implicitly thinking it converges to a limit, it converges to a single number. So if we wanted to use the definition of convergence, the basic definition, so we would say converges to some L, and here you have to make a choice. You have to guess what it converges to. Luckily, because you guys have already studied in high school the formulae for convergence, you can guess what this converges to, right? You can usually guess that in this case, this is going to converge to 1/2, right? So you guess that this sequence is going to converge to 1/2. So what you need to show is that there exists, so for every epsilon greater than 0, so it doesn't matter how small epsilon is as long as it's positive, for every epsilon greater than 0, there exists a sufficiently large integer, this is some integer such that Sn minus 1/2 absolute value is less than epsilon, less than epsilon. Okay. So, well, let's just say less than epsilon. So now the trick is, the basic question, whenever someone asks you to prove convergence, is firstly, guess the limit. Secondly, give an explicit reason for there existing such a n of epsilon. You have to find such an integer for every epsilon. Okay. So in this case, it's not too hard, right? So if you want to find such an integer, you just plug the thing into here. So what does that give you? It gives you n plus 1 over 2n plus 1 minus 1/2 absolute value should be less than epsilon. So what that tells you is 2n plus 1 2n plus 2 minus 2n plus 1 over 2 times 2n plus 1 absolute value is less than epsilon. These things cancel, and you're left with 1 over epsilon is greater than or equal to 4 times n plus 2, right? So that tells you something like this. So that tells you that absolute value of n, that n has to be larger than 1/4 of 1 over epsilon minus 2. Okay. Now notice that here I'm just doing reverse engineering, right? Why am I calling it reverse engineering? Because this thing here is the integer I want. This is my n epsilon, and I want to find it. So notice that every step over here is reversible. So if I choose any integer that's larger than this, then I'm guaranteed that my s of n is going to be at least epsilon close to 1/2, right? So this is just sort of reverse engineering the answer that we want. But this is generally the procedure that we want. This is the procedure that we want you to follow, because this is now a proof that your sequence is indeed converging. This is telling you that after this point, after your small n is larger than this capital N, doesn't matter where you look, everywhere, it's a proof that everywhere for all sufficiently large n, your Sn is going to be epsilon close to a half, right? And that is indeed the definition of convergence. Now, sometimes it's hard to guess what the limit is. For example, in question number 4, we'll see a sequence for which it's hard to guess what the limit is. So there's a different definition. I mean, there's a different definition of convergence that we can prove is equivalent to this definition of a convergence. In that different definition, the Cauchy's convergence for criterion, you do not need to know the value of the limit. You can prove that a sequence converges without even knowing the limit. Okay, so we'll see that in question number 4. Now, continuing on with the remaining parts of question number 3. So let's look at question 3b. So let me just get this unstuck. Okay, so in question 3b, we ask you, okay, so here it's a more abstract question. So here we're asking you, suppose an and bn are both convergent sequences, and we are telling you that the limits are capital A and capital B. Some sequences which are convergent and the limits are capital A and capital B respectively. Then we're asking you to prove that the product of convergent sequences is convergent. Okay? And again, this is a thing that you take for granted because that's what you've studied in high school. But all of these facts require proofs, and this exercise is to begin to get you to think about how to prove something like this. Okay, so how would you prove something like this? So let's try. So let's say, okay, so we know that the sequence AN converges to A. That's what you've been told. BN converges to B. And what do we want? We want to show that for all n, so for all epsilon greater than 0, there exists some capital N of epsilon, such that for all n greater than capital N of epsilon, AN BN minus AB is less than epsilon, right? That's what we want to prove. So now that's a little bit tricky because you know something about AN being getting close to A, BN getting close to B, but how does the product of these two numbers behave? Not immediately clear. Okay, so let's begin with a few facts. So if AN is converging to A, what do we know? We know that for all epsilon greater than 0 exists, let's call it NA of epsilon, such that for all n bigger than capital N of epsilon, AN minus A is less than epsilon, right? And you can also find something similar for all epsilon greater than 0 exists capital NB of epsilon, some different integer, such that for all n greater than NB of epsilon, BN minus B is less than epsilon. Okay. Now, let's note a couple of things. It's not clear that these two integers are the same integers. They could be different, right? It could be that one sequence converges more quickly than the other sequence. Not clear. So ideally, you would like both AN and BN to be pretty close to A and B respectively, right? So here's one of the tricks. One of the tricks can be that we just choose the maximum. So define, let's say, N A comma B of epsilon to be the maximum of N A of epsilon and N B of epsilon. Okay. So in this case, we are guaranteed that both the sequences from this point onwards, from this integer onwards, they're at least epsilon close to En and Bn respectively, right? Now let's notice another thing. So okay, so if we try doing it now, An is pretty close to A, Bn is pretty close to B. So let's see what happens. And here's another trick you can use. You can use the trick by saying, okay, An Bn minus An times A plus An times A. So you're adding and subtracting the same term minus AB. Okay. How did I do this? So I'm just rewriting An Bn minus AB is equal to this term over here. Okay. How did I choose to add and subtract the terms in the middle? Well, it's a trick, right? to know these tricks. But really, what this will allow us to do, you can maybe see, is that in the first case, I will be able to pull, oh, my mistake. I should add and subtract something like an times b and an times b. So now what will this allow me to do? It will allow me to pull the first two terms together and take an out in common. It will allow me to pull the second two terms out and take b in common, right? So if I do that, and I can use the triangle inequality, so then this tells me this is less than or equal to an times bn minus b plus b times bn minus b times an minus a, right? So if you think about it, okay, so we are in pretty decent shape, right? Because what that tells us is, okay, so we already know we've chosen our integers such that bn minus b is pretty small, it's like epsilon. We've chosen our n such that an minus a is also less than epsilon. But what this will give us is not quite what we want, right? It will give us something like, so this quantity is less than or equal to some okay, but I don't quite know what an is, so I'm going to bound it from above by a plus epsilon. So what do I know? This whole quantity is less than this times epsilon plus absolute value of b times epsilon, right? So so here this shows us that we're not quite where we want, right? So it's a small quantity, but it's not quite the same small quantity that we want. So we just do another trick. We say, okay, we choose an even smaller epsilon for the original ones. So choose an even smaller epsilon. Let's call it epsilon prime, such that these quantities are less than epsilon prime. And then we have a quadratic equation, something like this. So we want this quantity to be less than epsilon. So now you can solve it, right? So I mean, it's again a reverse engineering thing. What do I want to do? I want to choose my initial sequences to be so close to the original limits such that the function of these sequences, an times bn, is sufficiently close, how close? Epsilon close to the product of their limits, a times b. Okay? And to find that, you can solve this quadratic equation here in a and b and substitute it. I mean, eventually it gets a little bit messy. You have to worry about, whether b is positive or negative or something like that. Or you can solve some quadratic equation. There's a formula. It's just a quadratic equation. You can just work it out, right? It'll be something like like, let's just simplify things. Let's just say absolute, a is bigger than 0, b is bigger than 0. You may have to worry about other cases as well, but assuming this, that you have a quadratic equation and you can solve for epsilon prime. Okay, but that's just a little messy detail. The points to keep in mind are that you have to start with the definition of the limit of a sequence. Given this definition, you know that each of the individual sequences are going to behave well, and then you can show that there, for example, the product converges, right? By similar processes, you should be able to prove that, for example, the ratio of convergent sequences is convergent. That if A converges and B converges, then an to the power of Bn also converges, right? All of these things that you take for granted, each of these actually requires a proof, and you can prove it by this method. Okay, that's question number 3b over here. Okay, now let's look at question number 3c. So 3c asks you to show that. So this was 3b. Now 3c asks you to show that S sin n over n converges to 0, and in particular it gives you a hint. It says, well, use a sandwich theorem to prove that that it converges to 0. So what does the sandwich theorem say? It says that if a sequence can be sandwiched between two other sequences. So what does that mean? Like if you have a sequence S of n, if your S of n looks like something like this, and if you can sandwich it above by some S prime n and sandwich it below by some S double prime n, so this is S prime n, this is S double prime n, and this is S of n. So it's always the case that this quantity is bigger than or equal to S of n, which in turn is bigger than or equal to S double prime of n. Then if each of these two converge, if S double prime, if S prime n and S double prime n both converge to the same limit, if both of these converge to L, if both of these converge to L, then that means S of n also converges to L. That's what the sandwich theorem tells us, right? So in this case, for S of n is equal to sine n over n, sine n over n. The choices are somewhat clear. S prime n you can choose to be 1 over n. S double prime n you can choose to be minus 1 over n. And by the standard definition of a limit, you can show, of course, that S prime n converges to 0, S double prime n converges to 0. And since sine n is always between plus 1 and minus 1, therefore the sandwich property is satisfied, right? Sandwich between the upper piece of bread and the lower piece of bread. So therefore, you have the sandwich theorem being satisfied, and therefore you know that it's converging to 0, right? All right. So we understand just the basic definition of limits. Now let's go on to question number 4, where I said, okay, so these definition of limits require us to know the actual limit, right? We have to somehow guess what the limit of the sequence is going to be. But sometimes a priori it's not immediately clear, right? Like if you did not know that this is the formula for e to the power for e, right? Like e, the Euler's constant, can be defined by the summation over here, 1 plus k equal to 1 to n, 1 over k factor, sorry, 1 to infinity, or 1 over k factorial. If you think about it, this is actually the definition of the limit of the definition for Euler's constant. So in this case, also you can guess the limit, but it's not so clear, right? If you did not have this piece of knowledge, you would not have been able to do it. If I give you something more complicated, you may not be able to guess the limit. So in this case, if you don't want to use this piece of knowledge, then how would you first of all prove that this sequence converges to begin with without knowing the limit, right? So that's where the Cauchy's convergence criterion is useful. As I said, it can be shown that this that sequences that this definition of the convergence criterion is equivalent to the original definition, and that's basically saying that so this is question number 4. So question number 4 says okay, so we are supposed to look at Cauchy's convergence criterion for Sn, where Sn is equal to 1 plus summation I is equal to k is equal to 1 to oh, we can't see it, k is equal to 1 to n of 1 over k factorial. Let me just adjust this so you can see it. Adjust this again. Okay, hopefully now you can see it. So S of n is like this, and now we're going to use Cauchy's convergence criterion. So Cauchy's convergence criterion says if for all epsilon greater than 0, there exist m and n, now two integers, m of epsilon and n of epsilon. Sorry. There exists capital N of epsilon, such that for all m comma n bigger than capital N of epsilon, absolute value of am minus an is let's just call this Sm minus Sn is less than epsilon. Then we say that the sequence Sn converges. Converges to what? We don't know, but you can prove that this is equivalent to the definition of the limit. Okay? Even though you don't know what the limit itself is, you know that the sequence converges. And this also intuitively makes sense, right? Because it's like saying, okay, the terms, every term after a suction point are close to each other. We don't know where they're going, but they're at least sticking together, right? So that somehow feels like it should be a convergence definition as well. And indeed, it requires proof, but we're not going to go there right now, right? I think one of the videos had it. So in this case, how do we use Cauchy's convergence criterion? So we notice that if I look at Sm minus Sn for this sequence over here, then that thing is nothing but 1 plus summation k equal to 1 to m
1 over k factorial minus 1 plus summation k, k equal to 1 to n, 1 over k factorial, let's just call it k prime, absolute value. Okay, and without loss of generality, let's say m is bigger than n. Yeah, even if m is less than n, you can just flip the two terms around, right? So it doesn't matter. You may as well just focus on the case when m is bigger than n. So if m is bigger than n, then this is nothing but these things cancel and many other terms cancel. This is equal to summation k goes from m to n, sorry, m plus 1 to n of 1 over k factorial, right? So now if you think about it, so since k is going to be at least 1, so actually each of these terms is decaying, right? So 1 over k factorial is larger than 1 over k plus 1 factorial, is larger than 1 over k plus 2 factorial, and so on, right? So therefore, you can say that this is less than or equal to. So first of all, actually, let's just do a few tricks here. So k is equal to m plus 1 to infinity 1 over k factorial. Why did we do this? Because, as you know, for example, in a geometric series, it's actually easier to find the limit or to find the sum of an infinite geometric series than it is to find the sum of a finite geometric series. Okay? And some of these terms are decaying so quickly, it doesn't matter if we add infinitely many terms because they're all very small. So let's just take the infinite summation instead of the finite summation. Okay, so now we've taken the infinite summation. Next, we notice that since the largest term corresponds to 1 over m factorial, so let's just write this out. So this is 1 over m plus 1 factorial, m plus 1 factorial, plus 1 over m plus 2 factorial, plus dot dot dot, right? Let's just write one more term, m plus 3 factorial, dot dot dot, right? So since it's like this, we can say, well, this is less than or equal to 1 over m plus 1 factorial times plus 1 over m plus 1 times m plus 1 factorial plus 1 over m plus 2, sorry, m plus 1 square times m plus 1 factorial plus dot dot dot, right? So here I'm just replacing every one of these terms with a larger term, right? Because instead of dividing by m plus 2, I'm just dividing by m plus 1. Instead of dividing by m plus 3, I'm just dividing by m plus 1 and so on, right? So I'm just replacing these things by larger terms over here. And then this becomes basically, this is 1 over m plus 1 factorial times 1 over m plus 1 plus 1 over m plus 1 square, sorry, 1 plus 1 over m plus 1 this square plus 1 over m plus 1 whole cube plus dot dot dot, and so on, right? So so here, this is a geometric series, right? This thing is a geometric series, and its limit you can compute. So the limit for this quantity is going to be 1 over 1 minus 1 over m plus 1, right? So you can figure it out. So overall, you'll end up with something like 1 over m plus 1 factorial times so what is this? This is m plus 1 over m, right? So this is m plus 1 over m. So this gives you 1 over m times m factorial, right? And 1 over, so and let's just do another trick over here. So we want a nice function, m factorial. Oh, you don't see the bottom. So by the way, none of the choices I'm making here are unique. Eventually, you just want to get some sort of a bound. So m factorial, we want this whole quantity, 1 over m times m factorial, to be less than epsilon, right? We want 1 over m times m factorial to be less than epsilon. So we want to find a value of m such that this equation is true, right? So we want to find a value. So we want to find a value of m such that this equation is true. So in this case, so in this case, what do we do? Well, we just use another trick. This term over here, 1 over m times m factorial, is less than or equal to 1 over m times 2 to the m. Why is that? Because let's just say m is bigger than 2. So in this case, sorry, 2 to the m minus 1. Why is this the case? Because m factorial is equal to 1 times 2 times 3 times 4 times dot dot dot, right? It's a product of many numbers, almost all of which are larger than 2, right? Except for the very first one, all the others are larger than 2. So if you replace by a smaller number, which is 2 times 2 times 2 times 2, except for the very first one, then we'll be choosing a larger term, right? So basically, we'll end up with something like 1 over m times. So this quantity is less than epsilon, okay? And then you can take logs and so on, and you can find a value of epsilon, which will give you something appropriate, right? So you can sort of invert this function over here, and you can find a value. Okay. Now notice, none of these tricks are unique. You can use other approximations over here. You can use other things, as long as you're able to find a bound of your integer n of epsilon in terms of your epsilon. Okay, that's the goal over here. Okay. All right. Let's proceed. All right. So question number 5 asks you for the Bolzano-Weierstrass theorem and to find a convergent subsequence. Okay. So this sequence over here is a little bit weird. Okay. If you so first of all, it's not clear what the pattern is. You have to look at it for a little bit. But if you look at it for a little bit, then you can begin to see the pattern emerge. So let's zoom in so you can see the sequence. The sequence is saying it's 1 over 2, 1 over 3, 2 over 3, 1 over 4, 2 over 4, 3 over 4. So 2 over 4 is actually the same as half. So this has already appeared in the past, right? Then 1 over 5, 2 over 5, 3 over 5, 4 over 5. So basically, it's like the denominator increases by 1, then the numerator goes through all the terms from 1 up till the denominator minus 1, right? So that's the sequence over here. Okay. So now we just had to figure out a way of writing this in some mathematical terminology, right? So if we think about it, what's happening is the denominator is taking some value k. Okay. So when does it take the value k? So let's say, so this is question number 5. The question number 5. So the denominator is taking some value k. So in particular, to take the value k, so let me actually just write out the sequence. So you have 1 over 2, 1 over 3, 2 over 3, 1 over 4, 2 over 4, 3 over 4, 1 over 5, dot, 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 2 over 5, dot, 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 right? So first there's one term like this, then there are 2 terms like this, then there are 3 terms like this, right? And so on. So to take the value 1, it happens after just 1 term. To take the value 2, it happens after 1 plus 2 terms. To take the value 3, it happens after 1 plus 2 plus 3 terms, right? So in general, if my n is less than or equal to k into k plus 1 over 2, and it's larger than k minus 1 into k by 2. How am I getting these things? So remember, k into k plus 1 by 2, that's the formula, which hopefully you remember, or hopefully you can derive it. K into k plus 1 by 2. Let me zoom out so you can see it. I'm sorry, I forgot I zoomed in. So if you look at this formula, k into k plus 1 by 2, that's the formula for the sum of integers from 1 up till k, right? So that's basically saying if my n is in this range, then the denominator, then Sn, the denominator is k plus 1, okay? And the numerator, I'm going to claim, is n minus k minus 1 times k over 2, okay? Why is that happening? So let's think again. So when k is 1, then that happens in the first term already, right? So when k is 1, then I have so is this equation true? So 1 into 2 by 2, so that gives us 1. So if k is 1, then this term over here is 1, this term over here is 0. So 0 is less than n is less than 1. So that's for the first part of the sequence. So when n is between 0 and 1, then the denominator should be k plus 1. The denominator should be k plus 1, which is 2. The numerator, in this case, just subtract out the left-hand side part of the equation. Okay? Subtract out this k minus 1 into k by 2. This is the sum of till k minus 1 terms. So k in this case is 0, right? You subtract that out. You can just try one more term. You can try, for example, 1 over 3, 2 over 3, and you'll see that this formula over here gives you the formula for the sequence. It tells you that when n takes different integer values, this is the value for that sequence. Okay? All right, so that's just some mathematical algebra just to figure out how to write the sequence nicely. Okay? But the next few parts of this question start becoming more interesting. So the next part asks you, okay, is S of n convergent? Is the sequence convergent? Okay, so let's see how the sequence is behaving. So first of all, you can notice that just by looking at this particular sequence, the values are always positive, right? They're never negative because all the terms here are positive. The numerators and denominators are positive. So everything is positive, and the numerator is always less than the denominator. So it's always less than or equal to 1. It's in fact always less than 1. So the sequence is actually always between 0 and 1. Every term in the sequence is between 0 and 1. Right? So it's a bounded sequence. And when you start drawing the sequence, so initially when n is 1, the sequence is half. Then, instead of drawing the sequence like this, let me draw it in this way. So this is like 0 to 1. So initially, the first point in the sequence is half. The next point in the sequence is 1/3, then 2/3, then 1/4, half, 3/4, then 1/5, 2/5, blah, 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 right? So I'm sorry, you weren't seeing it. I really should be keeping an eye on the thing. Okay, how about every time you can't see the screen, you can't see what I'm saying, just make a noise. So then I'll know that you can't see it. Okay, I'm sorry. Sometimes I don't look at the screen, so I don't quite realize that you're not seeing what I'm drawing. So please let me know. Okay. So, but basically, as you can see, like every time the k increases, then the smallest value of k becomes close to 1, and the largest value of k becomes the largest value of n within that range for that fixed value of k becomes close to 1. The smallest value of n for that fixed value of k is close to 0, right? So it really looks like it's not converging at all, right? It really looks like it keeps cycling between 0 and 1, getting closer and closer to 0, closer and closer to 1, right? So it really looks like it's not converging. Okay, so how do we show that a sequence is not converging? We have a guess, or at least I guess that it's not converging, right? Because it really doesn't look like there's any particular value towards which it's headed. So we need to prove that. We need to prove that it's not converging. So let's just find two different points. So what do we need to show? So we need to show that so if the sequence is converging, so let's do this slowly. So if the sequence is converging, then we would be able to show for all epsilon greater than 0, there exists a capital N of epsilon such that n bigger than capital N of epsilon would imply that S of n minus L is less than epsilon, right? So suppose this was happening, then we would always be able to find something like this, right? We would always be able to find something like this, or instead of using this, because here we would need to guess the definition of the limit, let's use Cauchy's convergence sequence. So S of m minus S of n is less than epsilon. We would always be able to find something like this. Okay, but I claim this equation cannot hold. So if we try to prove this, I can always find sufficiently large m and n. I can always find sufficiently large m and n such that this equation cannot hold for sufficiently for some fixed epsilon bigger than 0. Okay. So for example, let me choose epsilon to be a half. Let me choose epsilon to be 1/2, and let me choose capital N. Okay, so let me choose epsilon to be a half. Now notice that if I look at this particular sequence over here, there are terms which are like 1/2, 1/3, 1/4, 1/5, 1/6, and so on. So there's an infinite subsequence which is converging to 0, right? Because 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on, that's converging to 0. There's also an infinite subsequence which is converging to 1. So if I look at 2/3, 3/4, 4/5, 4/5, 5/6, and so on, that subsequence is converging to 0, right? So the point is, doesn't matter which capital N I choose, I will be able to find some term larger than that capital N, where the term in that subsequence is converging to 0, okay? And also a term in that sequence where the corresponding term is converging to 1. Right? So in particular, I'll be able to, for any capital N I choose, I'll be able to find AM larger than, where M is larger than capital N, such that AM minus 0 is less than epsilon, like the absolute value of AM minus N is less than epsilon. Let me write this down. So, so my claim is basically for all capital N, I will be able to find N can find N such that there exists Sn minus 0 absolute value is less than let's say 1/4. Okay, so I just want to disprove it for epsilon greater than a half. So let me just choose an epsilon which is less than 1/4. Okay, so basically I want to find a term which is at least 1/4 away from 0, where the bound from 0 is at least is no larger than 1/4. Okay, and I can also find n prime such that absolute value of Sn prime minus 1 is less than 1/4. Okay, so in this case, I would be able to show, therefore, by the triangle inequality, that Sn minus Sn prime has to be larger than 1/2. Right? Because Sn is less than is 1/4 away from 0, and Sn prime is 1/4 away from 1. So there's no way that Sn and Sn prime are closer than half together. Okay. So I'm skipping a few steps here, again in the interest of time. Look, it's a short class, Wednesday, right? I do want to make a couple of other points in this question, but I believe you can fill in the gaps a little bit over here because you've already seen the other proofs of limits. The point is, here you're able to show by Cauchy's convergence criteria that it cannot be satisfied. That doesn't matter how you choose, how large a capital N you choose. You can always find terms beyond that capital N such that there are some values of the sequence which are very close to 0. There are some values which are very close to 1, and therefore these two terms are very close to 1. Okay. So that's how you would show that this sequence is not convergent, right? All right. Now, parts C and D, we've already sort of guessed, right? So the supremum is somehow the largest limit, the limit of the largest, the largest limit in the set. So if I look at all sequences which converge, so all subsequences which converge, what is the largest limit in the set? And we've already sort of noted that none of the values here is larger than 1. And we've also noted that there is a convergent subsequence which is getting closer and closer to 1, right? So notice that we've already noted that there are terms like 2/3, 3/4, 4/5, 5/6, and so on. So this subsequence is converging to 1. So therefore, the supremum is indeed 1, right? That's the largest possible limit in this of any subsequence here. Similarly, the infimum, the smallest possible limit is 0, right? So here we have the supremum is 1, the infimum is 0. The Bolzano-Weierstrass theorem, what does that ask? It says if a sequence is infinite sequence is bounded, then the Bolzano-Weierstrass theorem holds. And in particular, the Bolzano-Weierstrass theorem says that that there must exist a convergent subsequence within this infinite sequence. Okay? So if you have a bounded sequence, then there must be a convergent subsequence over here. And in particular, in this case, I'm going to leave the last part of this question open for you guys. We are basically out of time, so that's the main reason. But it's also one of the, it's the cliffhanger for today, right? It's a suspense question for today. So what is the set of limit points for this sequence? Okay. So any guesses, anyone? If you want to make a guess, we'll just ask for a guess, and then we'll continue tomorrow with this question. So what is the set of limit points for this sequence? William, you wanted to say something?
Which sequence?
So the original sequence, the sequence is this sequence over here, right? We have a sequence which is this crazy sequence. It keeps jumping around between 0 and 1. So we noted that, for example, you can find a subsequence half, 1/3, 1/4, 1/5, 1/6, which converges to 0. You can find another subsequence which converges to 1. You can find another subsequence which converges to a half. Can anyone think of a subsequence which converges to a half? So for example, we noted 1/2 is the same as 2/4, is the same as 3/6, is the same as 4/8, right? And so on. Okay, so looks like you have a guess. Pi. So William says pi. Not everything is pi. In fact, pi is larger than 1, so it cannot be within the subsequence, right? Any other guesses? Yes. All rational numbers between 0 and 1, says Wayne. So, good guess. I claim it's even larger than that. 2 pi. 2 pi. So it's billion. Okay, so Wayne is onto something. Wayne is saying all rational numbers between 0 and 1, which is an interesting guess, right? I claim it's even larger than that. I claim it's all real numbers between 0 and 1. So you can find subsequences which converge to, for example, 1/8, 1/√2, right? And so on. Okay. Think about that. That's the cliffhanger for today. So think about why you can find any subsequence you want in here, converging. So you can, for any real number between 0 and 1, you can find a convergent subsequence within the sequence. Think about that. All right, class is over.